Hello. It's wonderful to be here. How do we observe the unobservable? How can we see something black against the blackness of space? How can we detect an object whose gravitational pull is so strong that not even the photons of light can escape it? These were some of the questions and some of the challenges that faced the Event Horizon Telescope, an international collaboration that was designed and built over the last 20 years explicitly to take the first photo of the shadow of a black hole. And this is our story. We begin over 100 years ago with Albert Einstein, who, in his general theory of relativity, taught us that we should not think of gravity as an attractive force between objects with mass, but instead that gravity was simply the consequence of the geometrical distortion of space-time. And that geometrical distortion was responsible for the paths followed by objects with mass and the photons of light as they travel through the universe. An elegant confirmation of this theory was performed 4 years later by Arthur Eddington and a group of astronomers who observed the sun during a total solar eclipse, and they were able to see a very small deviation in the path of light between the apparent position and the true position of these background stars. And this was exactly in agreement with the predictions of Einstein. This was the first confirmation of the theory of general relativity. Another important moment in this story, 1 year later after the publication of the theory of general relativity, is the work by a German astrophysicist mathematician, Karl Schwarzschild, who found an exact mathematical solution to the equations of Einstein. And in this solution, he predicted the existence of an enigmatic, exotic object, a singularity, an object infinitely small, but with a mass sufficient to completely distort space-time and create an event horizon, create a region from within which photons of light cannot escape, creating a shadow, creating a black hole. But how can we see something that's black? If no light emits from a black hole, how can we see it? We need a source of light. We need something to illuminate the black hole. In the case of supermassive black holes that reside in the centers of galaxies, the hot ionized gas plasma that is very bright at millimeter wavelengths is able to produce that source of photons. Some of these photons are gently deflected as they travel towards and past the black hole. Others are caught and double back towards us, and other photons are captured into circular orbits. The result of the movement of these photons of light is to create a shadow, essentially a silhouette superimposed on this background light of millimeter wavelength photons. So this is the signature of a black hole, a dark shadow surrounded by light. The size of the shadow, the diameter of the shadow, is exactly the square root of 27 times the Schwarzschild radius. In other words, the size of the shadow is about 2.5 times the size of the event horizon. The shadow is a lensed, magnified version of the event horizon. The problem we have is that event horizons are incredibly small. If we consider the Earth and take the mass of the Earth and compress it into a volume sufficiently small to create a black hole, that black hole has an event horizon that's just 2 centimeters in size. If we take the sun and compress the sun into a volume to create a black hole, the event horizon is only 6 kilometers in size. And in the most extreme case of a supermassive black hole, a mass 6 billion times the mass of our sun, 6,000 million times the mass of our sun, then its event horizon is approximately the size of our solar system. The problem is that these objects are far away, the event horizons are small, and so the angular size of the shadow and of the event horizon on the sky is just a few tens of micro-arcseconds. That's the size of a golf ball on the surface of the moon. That's the size of the object we have to detect. That's the size of the event horizon of a supermassive black hole. So how do we do this? We understand there's a relationship between the size of a telescope, between the resolution that we need to see an object and the wavelength of light. And if we put those numbers together, we find that we need a telescope 13,000 kilometers in diameter. Enormous. Fortunately, that's the size of the Earth. So all we have to do is build a telescope the size of the Earth, make observations in the millimeter band, and in principle, we can detect the event horizon of a supermassive black hole. This is the Event Horizon Telescope, an international collection of millimeter wavelength telescopes distributed over a number of countries in Antarctica, the United States, in Chile, in Spain, and importantly, here in Mexico, 100 kilometers from where we're sitting today, the large millimeter telescope, the Gran Telescopio Milimétrico, on the summit of Volcán Sierra Negra. Not only is the event... I feel like that too, thank you. Not only is the Event Horizon Telescope an international collection of telescopes, millimeter wavelength telescopes, it's also an international collaboration of scientists, more than 200 scientists working on the analysis of the data, the production of new theories, new models, simulations, testing and interpreting the data and publishing the results. But how do we make these observations? Well, we use an ingenious technique called very long baseline interferometry. We're able to point all of these telescopes simultaneously at the black hole. The light from the black hole arrives at slightly different times at each telescope. But we use atomic clocks, very precise clocks, to time the exact moment of arrival of light at each of these facilities. We record these data on disk drives. We send those disk drives to a central processing unit, a correlator, effectively a supercomputer, and then we combine in software the light from all of these telescopes, synchronizing them with the timing signals from these atomic clocks. That allows us to create a planet-sized telescope. We also take advantage of the rotation of the Earth. You see here in the red lines, these are the baselines connecting pairs of telescopes. And so as the Earth rotates, we're able to fill in more of this synthetic planet-sized telescope. So this is the technique we used. The Event Horizon Telescope is essentially a telescope 13,000 kilometers in diameter. So what did we do? In 2017, the telescopes of the Event Horizon Telescope pointed simultaneously towards the Virgo cluster. And in the Virgo cluster, specifically, we looked at a galaxy called M87, a giant elliptical galaxy 55 million light years away. As we looked deeper and deeper into this galaxy, we could see not only the host galaxy, but we could also begin to see the jet, this powerful, luminous, collimated jet, ejecting fluids, relativistic fluids, close to the speed of light, getting deeper and deeper into the core of the galaxy, looking for the cause for this power, until finally we saw the monster, the supermassive black hole, the shadow of a black hole, the evidence that we've been looking for. The evidence we'd been looking for, the result of 20 years of work captured in this image. It looks like a simple image. It's a shadow surrounded by a ring of light. But the size of the shadow, the shape of the shadow, is exactly consistent with the predictions of Einstein, the theory of general relativity published over 100 years ago. To try and put this in context, the galaxy, the elliptical galaxy that you saw, has a size of about 80,000 light years. That's the size of the bar that you see on the left-hand image that shows the galaxy and the radio emission extended beyond the scale of the galaxy, powered by this single nuclear black hole. But in order to see the event horizon, we had to take an image that magnified essentially this image by a factor of 7 million. That's like using a microscope. We use a telescope, of course, but it's equivalent to using a microscope with a magnification factor of 7 million. That's what was required to see this shadow. You may have noticed that the ring is not uniform in brightness. The southern part of this ring is brighter than the northern part. The reason for that is that the relativistic fluid, this hot ionized gas, close to the event horizon, is traveling with relativistic speeds, speeds close to the speed of light. And when that gas is moving towards us, it gets a boosting, it gets an amplification, a Doppler boosting. And conversely, the light that is moving away from us is dimmed. So in this way, we're able to understand the direction of rotation. We're able to actually say that the plasma is rotating around the black hole, and that allows us to argue that the black hole itself is spinning. So this is now part of the ongoing research to try and understand more about the nature of the spin of the black hole and the interaction between that spin and its surrounding plasma. But we're not done yet. In 2020, we will continue these observations. We will include 3 more telescopes, one in Greenland, one in France, and a second telescope in the United States. So we will have 11 telescopes participating in March of 2020. Of course, the LMT, the Gran Telescopio Milimétrico, will be there as well. But that's still not enough for us. We're ambitious, we want to do more, and so the plan is that by 2025, we will have more telescopes in more countries, creating more collecting area, larger separations, which means longer baselines, and also changing some of the instrumentation so that we can operate at higher frequencies, which also will increase the angular resolution. So we will have the opportunity to now study the interaction between the jet and the black hole, the symbiotic nature between them, but importantly, we will be able to make movies. We'll actually be able to see the relativistic fluid circulating around the event horizon. This will be a different test of Einstein's theory of general relativity, not only due to the bending of light, seeing the shadow, seeing the bending of light and the distortion of light through the strong gravitational field, but actually tracing the motions of relativistic fluid close to the event horizon. So what have we achieved? What is the message? We observed the unobservable. We took an experiment that could take a photo of a black hole, objects in our imagination, exotic, enigmatic objects that exist in science fiction movies, in books, in songs, in art. And this was only possible because of a large, talented, ambitious team of scientists, but also because of a strong commitment and a long-term commitment from funding agencies and from foundations to financially support this project over many years. We published this image on April the 10th. We announced the result in multiple simultaneous press conferences around the world. But what we did not expect was the reaction the following morning. This image appeared on the front page of almost every national newspaper in the world. Estimates vary, but it's thought that of order a few billion people have seen this image. And so with this publicity, there comes great opportunity, but there also comes great responsibility for us as scientists to use results like this, to use this image to promote education, to promote science, and importantly, to inspire the new and young generation of scientists, engineers, and technicians. I hope many of you here in the audience. But we also have to persuade and convince governments and politicians to support these projects. These ambitious projects, large-scale projects, long-term projects that may not succeed. These projects may fail because they're so ambitious. But when they succeed, we're able to achieve something important, something impactful, something epic. We're able to achieve an epic result. And I hope that the EHT, the Event Horizon Telescope, in some small way has contributed to this. Thank you very much.